Good morning, everyone, depending on where you are. It's the top of the hour, and I'd like to get started. Thank you all for joining us for today's AIA presentation of construction joint sealants, a critical part of the building envelope performance. Presenting today will be Patrick Rainey, who is our architectural representative in Northern California and Reno, Tahoe area, and Isaac Sorensen, who is our architectural representative in New York City and the general proximity. Before we get started, just a couple things. Please take the time to make sure your microphones or phones are muted to help eliminate feedback. Sometimes they pop on and off. So if you'd be so kind as to do that and possibly shut down your video cams to help eliminate bandwidth use. This is an AIA presentation. Continuing education certificates will be sent out to those of you that registered and attended. We will also be sending notification to AIA for those of you who have provided your AIA numbers. And lastly, we have a chat box, if you notice on the bottom, and we will attempt to answer any questions via the chat box during the presentation. If we can't get to them during the presentation, we will certainly make every effort to get back to you with an answer. So bear with us on that. Hopefully we have a little bit of time at the end to answer some questions. And with that, enough from me. Patrick, take it away, please.
All right, thank you, and good morning or good afternoon, whichever the case may be. As Roger just said, I'm Patrick Rainey, and I take care of Northern California and Northern Nevada for the company. My colleague Isaac Sorensen will be along a little later to take over the presentation. So with that said, let's get into today's topic. We have a number of topics available for future presentations as well, but today we will be talking about construction joint sealants, which play a critical part in the building envelope performance. This presentation is intended to explain the basics of joint sealants and introduce the options that are available, the intent being to help specifiers and end users choose the correct product for the project. Well, who are we? Well, the W.R. Meadows company started in 1926 in Elgin, Illinois. Our company is family owned and operated to this day. And we are very proud of the fact that in just a few short years, we will be reaching our 100th anniversary, which of course we are very excited about. We are now headquartered in Hampshire, Illinois, and we currently have 12 manufacturing facilities and 4 warehouses strategically located around North America. And that includes Blue Ridge Fiberboard, which is a part of the W.R. Meadows family. Next. So here's a map of our various locations that we have in place to serve you in the US and Canada. But I also want to mention that our products are available worldwide. So wherever you may have a project, we can certainly be of help. We started with one product back in 1926, which was asphalt expansion joint. And we now offer over 300 products to help protect your design structures. From our Division 3 offerings that include expansion joint materials to structural and surface concrete repair materials, epoxies and grouts, to our liquid line that includes curing compounds, curing and sealing compounds, and sealers for decorative concrete, to our Division 7 products, starting with underslab vapor barriers and retarders, to air, water, and vapor barriers for above grade applications, to our below grade waterproofing systems, and with the soundproofing and insulation board products from Blue Ridge, we have a full line of products to help in protecting the building envelope. And again, just a quick reminder that this is an accredited AIA presentation, and all registered architects are able to collect a learning point for it. So as Roger mentioned earlier, please be sure we have your information, including your AIA numbers, so that we can make sure you receive credit for the session today. So to take a look at our learning objectives, we will be looking at terminology, sealant purpose and applications, common problems that can occur joint design, critical success factors to successful installations, and also material selection. So as we proceed through the presentation, we will take a look at each of these topics. So just to take a quick look at the history of joint sealants, they were first used in prehistory and made up of basic materials of mud, grass, and reeds. The next step forward introduced other materials such as pine and birch pitch, bitumen, wax, tar, etc., and a few other interesting items there. Then a further progression in the 17th century when an early form of caulk was used to seal window glass. And by the 1920s, the first polymers were developed and used in sealants. So we can see from all this how the technology has changed and advanced over time and what these advancements mean to the construction industry today. So let's look at the important distinctions to be made between a caulk and a sealant. Next. Thank you. By definition, a caulk is any low to intermediate performance compound, typically lower quality with limited service life, usually 3 to 5 years, while a sealant, on the other hand, typically refers to a high performance compound with better quality ingredients, a typical service life of 10 to 20 years, little shrinkage, and excellent weatherability and UV resistance characteristics. So some further sealant terminology definitions to look at here involve modulus, which basically means the ability to move. Low modulus sealants are very elastic and can accommodate more movement without failing. Medium modulus materials are used for the majority of sealant applications as they are looked at as a more general purpose type of a sealant choice. And high modulus sealants are stiffer, denser, and less stretchy, so they are well suited for non-moving joints. And these products are commonly used for sealing glass to window and door frames. So next, let's take a look at the purpose of joint sealants. They are used to seal penetrations in joints, also to prevent water and moisture, as well as snow and ice from getting into our building's interior spaces. And if this occurs, a number of bad things can happen, as you can see here, including what we like to refer to as the M word, meaning mold, which is when the lawyers usually get involved, which, of course, nobody wants. So the further purpose of these sealant products is to accommodate movement, function as part of an air barrier system, as well as a vapor retarding system, and to contribute to acoustic control. So what we are trying to accomplish is to prevent water, air, vapor, and sound infiltration into our building. So in terms of typical applications, this slide lists some of the basic usage areas for joint sealants. These include high-rise and low-rise commercial buildings, plaza decks, tilt wall, institutional, and airports. And some further application areas. Next. There we go. And some further application areas are bridge and highway projects, parking lots, sidewalks is a very common application, as well as parking decks and so forth. Next. So here are some of the substrate types that are typically sealed with joint sealants. These can include concrete, masonry, brick, wood, EIFS, stucco, and so on. So as we can see, joint sealants come into play in just about every type of project that we would be involved in. So this next slide is an explanation of ASTM C920, which is the primary ASTM used for polyurethane joint sealants, and these are the test methods that are used. Just to take a quick look at these, ASTM C719. This is the standard test method for adhesion and cohesion of elastomeric joint sealants under cyclic movement, and this test measures movement capability. The ASTM C661, this is the standard test method for indentation hardness of elastomeric type sealants. This test is a simple measure of the indentation hardness of a joint sealant, meaning it tests for sealant hardness, and the lower the number, the harder the sealant. The next one listed is C679, and that is the standard test method for tack-free time of elastomeric sealants. And lastly, ASTM C794. This is the standard test method for adhesion in peel of elastomeric joint sealants. This is a measure of the ability of the cured sealant to maintain a bond to the substrate under severe peel conditions. So this slide indicates the grades and types of polyurethane joint sealants. Listed there, type S is single component, type M is multi-component, grade P would be pourable or self-leveling, NS stands for non-sag, and class 25 indicates a total movement capability of 25%, meaning 12.5% elongation and 12.5% in contraction. So ASTM C719 addresses movement capability and has 5 classes. The majority of sealants used in construction today fall into either the 25% or 35% class typically. The 100/50 class indicates the material can elongate 100% and contract 50%, which is quite an extreme. So we'll take a look at some joint sealant application photos in these next few slides. This is an example of an expansion joint application in precast concrete. Our next photo shows an example of an expansion joint application between different building material types, in this case concrete to ephes. This photo shows examples of expansion joints between differing building material types. In this case, aluminum window frame units and masonry, and also metal cladding and ephes. And here's an example of an expansion joint in masonry veneer. And this next photo is a sealant application showing an expansion joint between metal wall panel and a high-rise building. This is an expansion joint where the vertical meets the horizontal. And joint sealants are commonly used in plaza decks and sidewalk applications. And this is, of course, a pool deck application where we can see the sealant that is above the water line. But there are also sealants that can be used below the water line in submerged conditions as well. And in these cases, a primer is always required. So this slide addresses some common problems associated with early failure of joint sealants, sometimes due to value engineering. A few of the key points to be made here are that we must have proper joint design, the proper material type for the condition, and proper joint preparation, meaning we need to clean, prime, and have the appropriate joint size. So in this next slide, we have a photo showing typical adhesive failure where the sealant debonds from the joint sidewalls. This is typically seen in flat work where the joint size is not properly designed or the joint prep was poorly done, which is usually the #1 cause, or the joint not being primed could be a factor as well. Here are some of the causes of adhesion failure. These include poor surface prep, contamination, as well as poor installation and priming. And some of the remedies that we have available to correct these problems would include grinding, as well as proper cleaning, priming, and tooling, which could include sawing the joint to help attain a proper joint configuration. So we've just looked at adhesion failure. So now we will take a brief look at cohesion failure, which occurs when the material tears down the middle of the sealant. Some of the causes for this type of failure are excessive movement that the sealant simply cannot handle, causing it to, quote, rip in the middle. Another factor could be three-sided adhesion, which means the sealant adheres to both of the sidewalls as well as to the floor or the bottom of the joint, which we do not want, and which is why we want backer rod used in that joint. This will be discussed in more detail a little later in the presentation. And lastly, inadequate thickness of the sealant itself, in many cases, turns out to be the cause of these types of failures. So this photo is an excellent example of cohesive failure. The typical causes being poor joint design, as well as improper width to depth ratio, and possibly the wrong sealant being used for the application. So the way to correct this type of failure from happening in the first place is with proper joint design, using the right sealant, and installing it correctly the first time. So in terms of substrate failure, there's really not a whole lot we can really do about substrate failures. Sometimes these types of failures can be attributed to joint sealant failure or vice versa. And in paving applications, should the concrete be unsound, the subgrade shift or wash out, failure at the joint face can occur. So at this point, I'm going to turn it over to my colleague, Isaac Sorensen, who will continue now with the presentation. So Isaac, it's all yours.
Thank you so much, Patrick. That was helpful. And this picks right up, of course, where Patrick left off, with critical design success factors being considered. So, of course, our standard recommended practice is creating the correct joint design. So recommended joint depth should be no smaller than 1/4 inch and no greater than 1/2 inch. And as you'll learn with that next bullet point, with proper joint design, we're looking for a 2-to-1 width to depth ratio, up to 1 inch in width. So of course, if we have the proper 2-to-1 ratio, the depth is never going to be greater than 1/2 inch, meaning that your joint at 1 inch wide would be 1/2 inch deep. Joint design within sealant movement capability. Patrick talked a bunch about the different ways that our sealants are rated in terms of their plus minus movement capability. We have to consider that once we've designed the joints in the 2-to-1 ratio, and considering the substrate, whatever that is for the movement, we have to allow the movement of whatever we're connecting with this joint. So if we have concrete or different types of materials, we have to consider technically each of their movement capabilities and what we're looking at when we do design that joint. Of course, a joint sealed at the lowest temperature will always experience compression, and a joint sealed at the highest temperature will always experience extension, and we'll learn a little bit more about these in subsequent slides. So joint sealants design factors for success. Of course, we talked about that 2-to-1 ratio. This is illustrating that. And then, of course, material selection, making sure that the modulus of elasticity is correct for the type of substrate that we are going to be connecting. And then also, of course, the design of the joint, whether it's going to create enough opportunity for our selected sealant to be correct. We can see at the top of this illustration as well, that green circle illustrating the backer rod that's put in there under the sealant. And it says correctly tooled shape of the sealant with depth of 1 to 2 width. Of course, the shape of the sealant itself becomes very critical in some of the types of joint applications that we put in place. Most notably, let's say a traffic joint sealant. If we have too much expansion or contraction, really when the material contracts and we have that sealant squished, for lack of a better word, the traffic going over that material may or may not affect it depending on the correctly tooled surface. So if we have a traffic joint that is not correctly tooled, it's going to actually stick up into traffic and essentially be damaged. without the correctly tooled surface. This next slide illustrates some of the failure possibilities with joint design, most notably with improperly placed or selected backer rod. And let's start with number 1 here. It says correctly tooled shape of the sealant with the 1:2 ratio. So we can see that that is proper joint design. Our adhesive and cohesive failures go way down in predictability here. And of course, in number 2, excessive depth, we're adding that depth in our joint design unsuspectingly just by pushing our backer rod in too deeply. So we're going to find that the pressures that this sealant is put up to change dramatically, and we're going to go over that in a upcoming slide. And then, of course, illustration number 3 there, insufficient depth of the sealant resulting from too shallow position of the backer rod results in cohesive failure. When we don't have that proper 2:1, we just don't have enough joint sealant there to actually protect the area that we're connecting. So joint sealant success factors, joint design, joint depth should be sufficient to accept backing material and proper depth of sealant. Backing material should be large enough to prevent floating or sinking of the material. And the idea is usually that with a backer rod compressed to be placed into the joint, it should be at least 25% expanding capabilities of that backer rod when you're placing it. So the number and spacing of joints is absolutely critical to performance. If you could imagine a 1-mile stretch of roadway with poured concrete, that concrete is going to expand and contract at a very, very calculatable rate. And if we don't place enough joints in that 1 mile of concrete, you can imagine the type of failure that we can undergo. So calculating the correct amount of space, the depth and width of each, the expansion and contraction is very important. Joints should be accessible for sealant placement. This seems pretty redundant, but if we consider maybe an outdoor pool situation where we have a deck, we have different coping and overlapping or cantilevered areas, we want to make sure that those joints that we decide to design are placed in an area where we can fully access them, where we can have proper joint filling and not be encumbered in our pursuit of creating a perfect joint that is accessible. There should be sufficient bonding surface for the sealant. Again, with that 2:1 ratio, we can do that, and considering, you know, no less than a 1/4 inch deep, that helps the surface area on the sides receive the sealant. And again, if properly prepped, we're not going to have to worry about the failure, either adhesive or cohesive failure. This here is an illustration, of course, of the expansion and contraction. You can see contraction on the left, that would be cold weather, and warm on the right, expansion. And we can see that with the 1:2, just let's consider that we had a proper joint design in the top left corner of the illustration here. The 1:2 becomes our ratio when our backer rod slips deeper into our design joint. So in that case, when we're experiencing the contraction, we're experiencing 94% strain on that sealant. Again, 1:1, we can expect that we're going to see about 62% in contraction. And then, of course, in proper joint design, in the 2:1, which is bottom left there on the left-hand side, we're going to see only a 32% strain in our sealant. And conversely, when we go to expansion in warmer weather, placed in the 1:2 ratio incorrectly, we're looking at 250% strain. That is enormous. And again, you can see that illustration of how an improperly placed and designed joint can then expose the sealant itself to failure by exposing it to whatever traffic is over top of the substrate, and so on and so forth. And then if we go down, of course, the 1x1 we're seeing that the strain goes down considerably, but still the sealant itself is exposed to possible failure. And then, of course, in expansion at our proper width to depth, 2 to 1, we're seeing that 20% of the strain. Now, again, the surface, the properly tooled surface, comes into play in this slide. We can see that if we were to expose our 2 to 1 joint in expansion in a warmer weather and we hadn't properly tooled it, that excessive amounts of that sealant would be exposed to the surface as well. Critical success factors for joint sealants, of course, material selection. Let's go through these bullet points. Will the selected material handle the anticipated joint movement requirements? Again, can't illustrate this enough, that making sure that the modulus of elasticity, the calculated movement of this joint are thought of ahead of time, then we can design properly our joints. Adhesion to substrate is probably the most critical element in the selection process, and as you'll see in some of the subsequent slides, we're going to go through the different types of sealants that are available to you in creation of your projects. Does the joint size allow for some sufficient placement of the selected materials? Again, if we stick to our no less than 1/4 inch and no in depth, and of course no greater than a 1 inch joint design, then we can allow for proper placement and movement. Will the product perform under the stated conditions of use? Again, that goes back to our first point made here. Is the history of application a success? So there are always new sealants out on the market. There's new chemistry that is taking place all the time. Let's go with some of the product categories within each of our building area categories that correlate to success historically. I like to call that legacy. Is there a legacy within a product group category for the stated area that you're going to be choosing this product for? So, of course, evaluate the supplier's resources. That's a little redundant. That goes without saying. And then third-party testing should confirm product performance. So these are the types of joint sealants that we are going to spend a little time going over. Latex, acrylic, butyl sulfides, STPEs, MS hybrids, polyurethanes, and silicones. Let's get into them. So beginning, let's look at latex. Latex sealants are water-based. They're easy to tool, easy to clean up, paintable, and relatively less expensive than other types of sealants. Some premium latex sealants may be appropriate for exterior use, depending on their appropriate service lives, and are rated for movements classes 12.5 and 25. Latex sealants may be best suited for interior finish applications. And there's a chart that I'm going to make available to you. I'm going to ask you to take a screenshot of it a little further into the presentation. But if we look at all of these sealant types that we're going over, we can essentially decide that latex and acrylic sealants are considered less than appropriate in commercial applications. Most of the latex and acrylic sealants are going to be used for our interior applications, around sinks, bathtubs, places where the service life isn't as critical and we can replace them. Some of the positives of latex are that they can be painted. That is probably the biggest reason that we use latex is interiorly, that they can be painted, and we would be using them on the interior. Acrylics are sealants are also paintable, but are solvent-based and more difficult to tool. They're used more in commercial and exterior applications than latex, and have very limited movement capacity, class 7.5. Acrylic sealants tend to be used in commercial construction, not so much, but in low movement joints where they are. Their cost tends to be in the low to moderate range, as well as the latexes. Again, I would think of these as interior application products. Then we get into butyl sealants. Butyl sealants are solvent-based. They're synthetic rubber materials demonstrating strong adhesion to a wide variety of substrates. They have excellent weathering characteristics, but tend to be stringy and difficult to apply. They generally have limited movement accommodation, usually less than 10%. Butyl sealants are sometimes used in curtain wall systems where adhesion to rubber materials is required, and the cost of butyl sealants tends toward the moderate range. And then as we get into the next group of sealants, this next group is sometimes called high-performance sealants and are most often used in commercial building assemblies. So polysulfides. Polysulfide sealants are particularly water and chemical resistant, but do not tolerate much cyclic movement for a high-performance sealant class, 12.5 to 25. Their use in buildings is common in swimming pools and other locations where submersion must be tolerated. Polysulfide sealants often require a primer, and they tend to be relatively expensive. Our next class would be STPE, or silo-terminated polyethylenes, and MS hybrids. Hybrids are relative newcomers to the sealant world. They have chains, silyl, that modify both silicone and polyurethane sealants. MS stands for silo-modified. Combining some of the strengths of each, the chemical profiles are better because they are solvent and isocyanate free. They have good UV resistance, excellent weathering capabilities, and excellent bonding, generally without a primer, to non-porous substrate. And of course, where they don't really assist in our commercial applications is in glazing. We need to avoid direct contact to glass. Polyurethanes, we're going to find that most of our commercial applications of sealant fall into this category. They are the most common sealant for a wide variety of substrates. Polyurethane sealants are tough, even abrasion resistant. Unlike silicone sealants, they can be painted. They have excellent adhesion and good movement capability. They're in usually the class 12.5, 25, and 50. They can be stiff and more difficult to apply and tool than silicone, and can be used in structural glass assemblies. As one of the high-performance sealants, including polysulfides and silicones, polyurethane caulks are relatively expensive. Again, they're good UV resistant, excellent weathering. We get a long life out of these products, and generally, without a primer, they are excellent bonding capable. So silicone. Silicone sealants are used in a wide variety of building applications because of strong performance characteristics. Their UV resistance, temperature resistance, and high movement capability, the class 50 to 100. Generally longer service life and continued flexibility over time, silicone sealants can have a strong odor and take considerable time to fully cure. They can be used structurally in glass assemblies. That's where we see them most commonly used. And cost for silicone sealants is in the high range. Pure silicone sealants are not paintable. So with most building materials, we ask, which one do I use? And the answer is, it really depends. Match the best liquid sealant to the substrate, the application, your budget, service life, compatibility to the substrate, and the material's constituency. So this is the chart that I was referring to earlier. I just want to say here that if you do have the capability to take a picture with your camera, or if you'd like to ask us after the presentation, this is not a proprietary presentation. We'd be more than happy to share the whole presentation with you, and of course this slide will come with it. But I like to hand this out when I do this presentation in person. It's a very helpful thing to keep on your desk if you are getting into sealant types, their uses and capabilities. As you can see on the bottom, we have a rating system from 1 to 4, 1 being not really or not rated, 2 being poor, 3 good, 4 excellent. And as you can see, those are the order in which I did get into the sealants themselves, going from latex all the way across to polyurethanes. And you can take a look at polyurethanes. Falls into the class 4 or excellent with most of these applications that are listed on the left, except for structural glazing. And then also, of course, in curtain wall applications. And then we get into silicones. As you can see, very few classes that fall into the poor rating for silicones. And of course, if we go all the way across back to our latex and acrylics, we can see that in a professional capacity, they're very wonderful for painting applications and for interior use. So hopefully this is helpful to you. Again, I recommend that you take a minute and screenshot this. You can always print it out, put it in your desk when you're at least starting to explore your interest in different types of sealants and where you might like to start looking depending on the application that you're going to pursue. So critical success factors with material selection. Again, I highly recommend the chart. Take a look at it. That'll put you into a place to at least directionalize your interest in sealants. We can look at some of the key material features for polyurethanes and silicones getting into the commercial application of sealants. Polyurethane superior primerless adhesion to porous substrates and very forgiving to less than pristine application conditions. I will put a little side note there that, of course, if you have contamination within your joint, if you have oil, if you have different types of things that have been absorbed into the concrete and it's not cleaned correctly, we'll get into some of that a little later, you're still going to have adhesive failure. Superior adhesion on the silicone side to glass, especially in applications subject to reflected UV at the bond line. And in polyurethanes, non-staining, no fluid migration from the sealant to porous substrates. And on the silicone side, where material does not chalk or discolor in the same way that polyurethane does over a long period of time due to the UV exposure. And you can see polyurethanes are used in submerged applications, paintable, and we don't see those capabilities in the silicones. Critical success factors, substrate prep, if done properly, would eliminate 95% of all the callbacks. Now, it can't be stressed enough. We talked about proper joint design. Preparation is the #1 cause of failure with a sealant application. We cannot stress this enough. If you do not properly design the joint and prepare the joint, the sealant itself, which is a really critical part of the building success, will not happen. So we need to take time to properly prep the joint. Applying the sealant into the joint, very simple process. Of course, it is usually what we're thinking of last, but if we take proper time to prep the joint, we can make sure that our success factors are high. So for porous materials, we want to make sure that we use an abrasive. If there's high pressure water used, we want to allow the surface to dry. If we're grinding or wire brushing or using compressed air, we need to make sure that there is no oil present in our compressed air system. The compressed air systems vary greatly depending on, homeowners types or commercial types of systems. Some of them incorporate oil into the coupling systems, and we don't want to get oil into our cleaning off of a porous substrate like a concrete. Non-porous, of course, with different types of metals. For sealants, we want the 2-rag method to clean it with a lint-free rag and absorbent. and solvent wipe followed by an immediate dry cloth wipe. Do not spread contaminants around. This is a very typical item that's used for, or tool that's used on a cutoff wheel or a grinder, as some people know them, for cleaning out a porous joint area. In all of our different types of prep material, mechanical methods, wire brushing, sandblasting, grinding, and sawing, we're going to have to remove the detritus afterwards and make sure that we have no sand, of course, in the sandblasting application. We want to make sure that we get all of the sand out of the joint. Sawing, of course, we want to make sure that whatever we're using doesn't have, if we're assisting our saw cuts with some kind of water, that it doesn't have oil in it. And if it did have oil in it, that we're cleaning it out correctly. But those are some of the material, some of the tools that we would use for our joints. In saw cut joints, in mechanical methods, you can see on the right, somebody sandblasting a joint to prepare it, get it ready. On the left, of course, we have a cutoff wheel, just preparing our joint and making sure that the depth is correct. And in both cases, again, we're probably going to use air or a vacuum to clean out the correctly designed joint before we place our backer material. Priming. Of course, priming is usually accommodated for submerged applications. And in priming, it seems simple. You know, in approaching priming, you can see on the right in this joint application that they've placed blue painter's tape on each side of the joint. I will say from my own personal experience that in placing painter's tape, it's often a false sense of security. If there is a high level of visual success that's being sought, you want to make sure that your painter's tape is fully adhered to the substrate so that if the edges of your brush catch the edge of the joint, primer doesn't end up on the surface. That's a pretty common problem. The other thing that can happen is if we're over applying a primer, we can get puddling. The other thing as well, of course, if we don't get the blue tape down to the substrate, both in applying the sealant and also in priming the joint, we can mess with the surface of the substrate. Many products perform without primers, most commonly used on horizontal and submerged, as I mentioned. Proper application with a brush, you want to prime both sides of the joint and prime the outside of the joint. Priming the outside of the joint may stain the substrate, as I mentioned. And you want to prime and put your sealer in there on the same day. So critical success factors regarding backer materials. Of course, we want to correctly place the backer material as earlier illustrated. Having improper, a properly designed joint with an improperly placed backer rod is just as much a failure possibility as an improperly designed joint without a backer rod. So as we place that backer rod, that's kind of the last line of defense, as it were, before we put in our sealant and make sure that it is placed correctly. So we want to obtain proper placement of the backer rod to prevent three-sided adhesion, as illustrated earlier, and provide support. So let's get into some of these backer rod materials. Closed cell backer rods. Closed cell backer rods will not wick moisture, making it suitable for joints with a high presence of water or dampness. Sealants, caulking, or other chinking materials will stick more easily to closed cell backer rods, which have a better bonding surface area than open cell backer rods. So closed cell backer rods, again, are just the structural component of the extrusion. It is basically trapping the gas in that extrusion into a cell and creating pressure, both expandable and contractible. And they don't tend to be as malleable as the open cell or bicellular rod. The open cell rod, primarily a foam material without a skin, Open cell is for sealant airing, which can reduce the drying or set time. And open cell backer rods may not be ideal for sealants that are susceptible to bubbling or of air escaping from them, because the backer rod material will release gas and air. Bicellular or irregular joint applications where self-leveling, flowable sealants are employed. Bicellular is also recommended with sealants where bubbling concerns are critical. It's an excellent all-purpose backer rod that may be used in place of most standard backer rod applications and are usually used for applications with high heat. Some of the DOT uses for backer rods with hot joint sealants employ the bicellular. And then also as a bond breaker, we can use backing tape, usually some kind of Teflon or polyethylene material, and we'll illustrate some of them in the further slides. So again, when you place your backer rod, there are tools for backer rod placement. We want to make sure that we utilize the tool if we have a very long horizontal joint that we're going to seal. Trying to get it correct with your fingers and measure all the way along the joint is not really a tenable situation. So there are very simple tools that are employed that will feed the backer rod through it. You set the depth, you roll it along the substrate, and it places the backer rod in the area that you need it placed at the correct depth. Again, we want to make sure that the rod is 25% larger than the joint width under compression to offer a good tooling base, and do not puncture closed cell backer rod. Again, you're going to have gases escaping. You may have your sealant susceptible to bubbling in that case when you have a punctured backer rod and you have some of that gas escaping and trying to work its way through the sealant material. As you can see here on the left, proper joint design with a backer rod. On the right, proper joint design with a backer tape. In both cases, that three-sided adhesion is going to be mitigated because with the expansion and contraction, our backer rod is going to move with the sealant. And on the right, with the backer tape, the expansion and contraction of the joint is going to be, there'll be a bond breaker at that tape line, and we're going to have the proper movement of the sealant, granted that we had properly designed with the correct sealant in mind. So for adhesion testing, we want to always test for adhesion. We're going to talk a little bit more about the adhesion test on the next slide, but you always want to put in your specifications that you do an adhesion test after the fact to make sure that whomever has applied the sealant into the quote properly designed joints, that they actually were a success, that they were cleaned properly, that the backing material was placed properly, and that we're going to have a long service life of our sealant. So a job site pull test is recommended, especially within your specs, to test the actual substrate on site. Document the locations and times. And then as you can see here, we're looking for cohesive failure within the bead. That's recommended. And the adhesive failure at any of the bond lines is not recommended. So for a job site pull test, we're going to take about 2 to 3 inches of a piece of the sealant and pull it at a 90-degree angle from the substrate. The sealant should not peel from the joint interface. Again, if you have more questions about this, we'd be more than happy to assist you. We have product group managers and so on that can help with specific, very technical understandings of proper adhesion if you're having failure on the site. But we want to see cohesive failure before we see adhesive failure. For specifications, it's important to note the different parts and pieces of a proper sealant spec. For this first one in references, ASTM standards, as they pertain to the relevant products. We want to make sure that we get the relevant products in there. 1.05 would be quality assurance and provide materials that meet local VOC requirements. This is an important part of where your job, essentially as a designer, making sure that you don't pick out a sealant that has improper VOC requirements for your local area. As most manufacturers are providing product globally, there are certainly requirements within each of your territories and areas that may or may not allow you to work with different types of sealants. 2.02 would be materials. Make point of ASTM types, the grade, and the class and the use. And then for 2.03 for accessories, make a point of the backer rod and the primer. If you need to utilize a primer or a backer rod, make sure that it is listed in this portion. For 3.02, reinforce joint prep and design requirements. Again, that is 95% of our success, having this proper joint prep and making sure that the joint is designed correctly and applied correctly. This is going to be very helpful in making sure that the service life of the sealant is truly a workable and helpful application. And then, of course, provide materials that meet your local VOC regulations. In summary, joint sealants provide a critical service to our building structural performance and longevity. There's a difference in performance between a sealant and a caulk, again, for easy use and remembering. Latex and acrylics tend to fall into the caulk category and are best used on the interior. And when we get into critical parts of the building, we're usually going to skew towards a sealant, and we're going to get into the butyls, polysulfides, MS polymers, silicones, and polyurethanes. Proper joint sealant design, preparation, and installation will lead to a successful application. Again, your job site, as far as your work and labor force is concerned, getting the sealant into the joint is the end, the end goal. And in many respects, slowing that process down to make sure that proper joint design is utilized, that we have the proper width to depth ratio, that we have our substrate cleaned correctly, and then, of course, having the proper sealant applied correctly and tooled correctly will lead to a successful application. There are many different types of joint sealants available. Make sure that you select the type that's best for your project, and I wish you much success. This completes the AIA portion of this presentation. Again, my name is Isaac Sorensen. I'm in the Northeast here, based in New York City. I strongly urge you to get in touch with us if you should have any further questions. And of course, we may or may not have enough time to answer all of your questions, but you can email us at info@wrmeadows.com. And the other thing that I would urge for you is to get onto our website. Take a look at our website. We have some wonderful resources for architects and engineers. If you go down to the bottom of the page, there's a tab that says for architects and engineers. You'll find BIM models, CAD details, guide specs, product data sheets. And then if you would like to reach out to us, we'd be more than happy to assist in providing free CAD details, working with you. We have 2 people on staff that work with our CAD details and will provide these to you at no cost. This is quite a successful program, and we look forward to helping you design your buildings. So, Roger, if you are still with us, maybe we have a little time to answer some questions. Looks like we've gone about 55 minutes so far. I don't want to keep any of you that are here that have been here for 55 minutes and have anything else to do. We'd be more than happy to stick around a little bit and answer some of these questions.
So, yeah, Isaac and Patrick, excellent job. A couple of things. There's a boatload of questions. I'm going to try to answer some of the more generic ones. Some we might want to answer privately or do some research to make sure we get the correct answer. Many of you have requested a copy of the presentation, and we will be keeping the chat line, so we will have all your contact info. We will be able to get copies out to you. Whether you requested PDF or video, we'll make sure we get something out to you or reach out to you. To answer a few of the questions that came up, I'm going to look at some maybe easier or more difficult or more subjective. One was, how is backer rod depth QC'd? There are tools available to control the depth of the backer rod. So there would be tools available, as I mentioned. In that vein, another one came back is would a pull test, job site pull test, be a cost add? I think the way to answer that would be if it's included in the specifications and quality control, then no, it wouldn't be a cost add. If you required it at the job site, then I think, yeah, it would be a cost add. So I guess there's two ways to look at that. My way of thinking, if you get it into the quality control portion of your specification, then everybody knows it's there and they can all plan for it. So
I'd also like to jump in, Raj, if that's all right, on this one.
Yep.
As a quality control measure, if you're placing it in the specifications and it's done before all of the sealant is placed, it seems a little obvious, but it is certainly important in placing, as almost like a mock-up would be before a floor is completed. You would want to make sure that your pull test is completed before all of the sealant is placed over the applied joints. Again, if you had, say, an application where you're doing multiple joint sealant and somebody had cleaned incorrectly, you would not want to place thousands of feet of joint sealant and then find out afterward that your pull test failed. So make sure that you use your pull test almost as a mock-up in your specifications to make sure that that is applied before, after the joints have been prepped, but before everything has been placed.
Thank you, Isaac. Yeah, that's a great point. Another question that came up, what type of backer should be used on pavement joints to prevent high heel shoes from puncturing the sealant, damaging the sealant, and possibly injuring the pedestrian? And that's a question that comes up repeatedly. In a situation like that, obviously having an expansion joint as opposed to a backer rod within the system so that you don't have that potential for shoving that backer rod down would be beneficial. The other thing to consider in that is the physical performance specs in terms of hardness could help prevent that, but that obviously has to be weighed with joint movement. So it's a difficult question to just throw a direct answer to, but having a full depth expansion joint so that you can't dislodge that backer rod with your high heels would be the best way, or maybe just recommend everybody wear sandals. Sorry, don't mean to.
I could jump in on that one as well. I think that in joint design, we often think, what are the least amount of expansion or contraction joints that we can place? And in this instance, we're discussing the opportunity for, a contraction where a joint sealant is forced up into a, transited area. And if we over-design our movement joints and we're placing, and we're worried about the sealant actually making its way above the surface, the more that we actually place, if you think about it, the less movement of that joint we're going to experience. So maybe over-designing the movement joints in places where we are concerned about the movement of that joint in contraction to be above the surface, we can mitigate that by adding joints?
Hey, Isaac, let me add one thing to that if I can.
Yes, please.
We also have, there are also sealants that will set up harder to accommodate foot traffic and things like that. So it's possible to design for a joint sealant itself that will set up harder when you're going to have foot traffic and those kinds of conditions as well.
Yep, absolutely. Thank you, Patrick. Well, we've just crested the top of the hour. I think we've touched on a fair number of the questions. There's a few we haven't gotten to, but we will definitely get back to you with those. For all of you who joined us, we thank you very much. We hope you found the presentation informative. For those of you who have requested copies, we will be getting those out to you, as well as your learning certificate credits and your AIA reports. Thank you again very much. Hope you all have a very productive and enjoyable rest of the week, and look forward to seeing you soon. Thank you very much.
Thank you so much.
Thank you, everyone, for joining us.
Thank you. Nice presentation.
Thank you. Hey. Yeah. Yeah. Can you hear me?